Hey guys, this is Mrs. Tran-Bloom. Welcome to Calculus, section 2.3. Alright, so we are going to start with continuity or continuity. So if I say it fast or if I say it slow, it's continuity. So the general idea of continuity is that you have any function at all. Okay, so let's spell it out. Any function. Let's call it y equals some function called f of x. Okay, that can be graph. That can be graphed without lifting your pencil or pen, whatever you're using. I would like for you to use pencil, please. Okay, so without lifting the pencil. Okay. It's called what's called a continuous function. Okay, so is a continuous function. Okay, so continuity, that's really what it means, right? You're gonna trace this function. You can't lift up your pencil. The moment you lift up your pencil, you would then have a hole, or you are jumping, called jumps, or asymptote. That's when you would lift up your pencil. Okay, so continuity is really a function that is connected. Okay, in shorter term, it's connected. Okay, no holes, no jumps. A jump function, it's sort of like the step function. You jump from one to the next. Or no asymptotes. Okay, so this is sort of a general idea. So now we have to get technical with it, right? Technical term of continuity is this. In calculus, we're going to use limits in a little bit, okay? So we have interior points. So interior point. Okay, interior point. If f of x is continuous, so f of x is continuous at some point x, let's call it c. Okay, if and only if the limit as x approaches this value of c of this function f of x also equal to f of c. Okay, so what this is saying that, hey, when I input in the c value, okay, let's just say that I want f of 5. So let's say f of 5 equals 10. Okay, it's continuous if I have the limits on both left and right. When I'm approaching this 5, should also be 10. Okay, so that's what it means to have an interior point on this continuity function. Another technical definition is we have the interior point, we have the end point, left or right. Okay, we have the end point. Okay, so we have, again, f is continuous. Okay, f is continuous at the left end point. Let's call it x equals a, if and only if the limit as x approaches a from the right, okay, of f of x equals to f of a. Okay, so if f is continuous at the left end point, okay, so let's give it a little sketch here. Okay, we're gonna sketch it right here. We're going to sketch this out. Alright, so we're going to have, here's a function, right? Just making this up. And here's the right. You know what? I want it to be a function, so I want to make sure it passes the horizontal line, vertical line test. Okay, that looks good. Let's call this x point A, and let's call this point B. Okay, somewhere in the middle, let's call it this point C. Okay, it doesn't matter. I'm just going to pick a interior point between A and B. So let's call it C here. Okay, so this is f of c. Okay, so the interior point says, hey, this is a function f of x, right, is continuous And here is a C point in the middle, okay, interior between A and B. So the limit as x approaches C from the left and x approaches C from the right is the same as f of C, which is true for this particular case, okay? So this is what it means to be in a continuous. Now the endpoint, we define both left and right, okay? F is continuous again, okay? At the left endpoint, here's the left, okay? Now if I pick A, so if x equals A, if the limit, okay, so here we go, if the limit that's coming from the right, okay, it's coming from the right, equals to f of A, which is actually true, okay? So now we're gonna go do the other side, which is the right endpoint, okay? F is continuous at the right endpoint. Since I have A and B, let's call it x equals B. If and only if the limit, okay, so here's B, as x approaches B from the left, okay, as x approaches B from the left of this function called f of x equal to f of B, okay? So this is then continuous from A to B inclusive, okay? All right, so we're gonna move up a little bit, and again, just go ahead and pause if I'm going too fast, okay? All right, let me just, since I'm taking a little pausing break, let me tell you a joke, right? A toddler joke, a 4-year-old joke. My triplets are 4 now. What is the difference between a teacher and a book? With the book, you can shut it up. Ha! See? Right? You can't shut up the teacher. Well, some teachers can't shut up. Some don't want to talk at all. Anyway, here we go. Continuous on an interval. As you know by now, I like to make fun of myself, so you can laugh, you know, at my my jokes or the jokes that I make about myself. Anyway, continuous on an interval. A function is continuous on an interval, okay, from A to B. A function is continuous on an interval inclusive A to B. Okay, so since I'm going to use this, I'm really going to talk about this one. So from A to B, if and only if it is continuous at every point on that interval. Okay, so that's really saying that from A to B, there are no holes, there are no jumps, and there are no asymptotes. Okay. Okay. So let's list a few types of discontinuity or discontinuity, however you want to say this, right? All right. Here we go. Let's zoom up a little bit. I want to look at the bottom. Ooh, here we go. Okay. The first type of discontinuity or discontinuity, okay, however you say it again, it's going to be called removable. Okay, removable, or AKA first semester, or in algebra trick we call that a hole. Okay, so let me give you a little sketch. Okay, here's, for example, here's some curve that I'm using, right? Let's just say that I'm not going to do the endpoints. It can be going on forever or not. And here's, let me put in a hole somewhere in the bottom. Somewhere, actually not in the bottom, in the middle. Okay, so this is a removable. Or I can have something like this. Oh, let's put in a hole right here. Okay, put in a hole right here, and right above it there is a closed dot. Okay, this is still a function because if I put my pencil on it, it passes the vertical line test. Let's try to make this not curving back, because if it curves back, then it's not a function. So like way, okay. And again, these are just sketches. This is a function, even though it's not continuous. it's still a function. It's continuous from here to here, wherever that is, right? This one is, this is a whole, and a whole is sometimes removable, okay? Not always, sometimes, okay? Here we go. And define. When the limit, okay, so when the limit as x approaches some value called c of f of x exists, okay? So that means the limit exists from the right and the limit exists from the left, but not equal to f of c, okay? So if you think about it, when I find f of c, for example this piece, right, f of c, let's just call it, this is a c value, f of c is above, right? But the limit is right here. Over here, I don't even have f of c. Think of these as two different functions, okay? So over here, I don't even have f of c. Therefore, the limit does exist. It's just not equal to the value of f of c, okay? All right, let's move on to, actually, I want you to, here are a few examples of what some removable functions are. So, examples, okay? In examples, rational functions, okay, rational functions typically has removable or wholes. Remember how in first semester, if we cancel the top and the bottom, that would create a whole, and that will be a removable discontinuity, okay? And then sometimes piecewise, okay, so piecewise. Okay, so these are the two functions, and it's really important to recognize these, okay? So important to know these. So when I give you a function, you want to think, hey, you know what? Is this removable or is it not? Okay. All right. So we're gonna go to jump. Okay. So discontinuity. Okay. That do not have removable, or this one I'm gonna spell out, not removable. So let's define this formally. When, oh, that doesn't look like when. Okay. When the limit as x approaches c from the right of the function, okay, when the limit as x approaches c from the right does not equal to the limit as x approaches c from the left of this same particular function. Keep in mind that they both exist, okay, but they're not equal to. So I'm gonna spell this out. Remember, okay, both limits exist, okay, and they do have a value, and equal to finite numbers. Okay, numbers. Finite number means not infinity. Okay. Okay. They both have, for example, the limit as x approaches c from the right. Let's just say 10 again, and the limit as x approaches c from the left. Let's just say 20. So 10 and 20 are finite numbers. Okay. So they exist, except that they're not the same as each other. Okay. So some examples of functions that have jumps are, the most obvious one is going to be your greatest integer functions. Integer function. Okay. Remember this one, f of x equals this. Okay. In your calculus book, I think they call it f of x equals int of x. Okay. And again, piecewise. Okay. And I don't know what the name of this is, but you're gonna need to recognize this. F of x or y equals x divided by absolute value of x. Okay, we've seen this before, and it typically this function looks like this. When x is 0, obviously we don't have any value for that. That's going to be undefined. But when x is 1, 1 divided by absolute value of 1 is still 1. So when x is 1, it's going to look like this, right? and it's going to go this direction. 2 divided by absolute value 2 is 2. But at 0, it's undefined, so it goes like that. Now, how about when x is negative 1? When x is negative 1 divided by absolute value of negative 1, and the denominator is positive, so I'm still going to have a negative value. Okay, so from here, and I'm going to go this way because when x is negative 2 divided by positive 2 is going to be still negative 1. But again, at 0, it's undefined. So this is a function. There's no name to this, but we've seen it before. This is look how it jumps. Okay, so this is not removable. And piecewise is really a lot of times it jumps from one to the next. Okay, we're gonna flip over to the next page, and again, please hit pause if I am going way too fast. Okay. Okay, so the next one is called infinite. Okay, so our next, here we go, infinite, which is also not removable. Okay, and in first semester we call it the vertical asymptotes. Okay. All right. So we are going to define this. When the limit of f of x as x approaches c does not exist, okay, because the limit as x approaches c from the right of the same function f of x, okay, equal to plus or minus, okay, infinity, okay, so plus or minus infinity, or the limit x approaches c from the left of this same function f of x equal to plus or minus positive or negative infinity, okay, or both. So let's look at a sketch. Okay, so let's gonna look at a sketch. Here we go. Remember cotangent function? Okay, so we have an asymptote here. We have an asymptote here, right? Cotangent function looks like this. Would you agree with that? Okay, so as x approaches 0 from the left, okay, as x approaches 0 from the left, looks like the limit is a positive infinity. Okay, as x approaches 0 from the right, okay, the limit is also positive infinity. Okay, so this is infinite discontinuity. Because according to this definition, it doesn't give me a finite number. It gives me an infinite number. Okay, so, and we've seen a couple before where I can also give you this. Remember, in rational function, okay, we have this piece. Remember this? Okay. As x approaches 0, right, from the left, it's going down, so there's negative infinity. As x approaches 0 from the right, it's a positive infinity. So, as you can tell, this is also an infinite discontinuity. Okay, so we're gonna, usually we have rational functions, so we can go, how about this? Examples, rational functions, okay, and some trig functions, okay? So, this is trig functions. Okay, so we'll just make a line right here. There you go. Okay. All right. The next one, our last one on this, the type of discontinuity is oscillating. Oscillating. Okay. So oscillating, and let's talk about when the limit as x approaches c of f of x does not exist. Okay. Okay. Because we can't determine it. Because cannot be determined due to the oscillation. Okay, and if you remember, oscillation, it's going to be like, here we go. Sometimes it's so fast, right? It's so fast that you can't really determine what the limit is, okay? So that's why oscillating is one of the discontinuity that, and this is not removable. The only one that's removable is a hole, okay? And the type of function that's going to be oscillating is normally trig functions, okay? All right. So we're going to go on to example 1. We have about 10 minutes of recording, so hopefully that's okay with you. Here we go. Example 1. Find the point of discontinuity of a y equals. This is a rational function, as you can tell. Okay. Usually, if you look at the rational function, you'll want to keep something in mind. Okay. Rational functions, light bulbs, right? Go on. Rational function. I should be thinking about, hey, holes? Question mark? Or asymptote, right? So these are the type of things that you need to think about when you see rational functions, right? So the first thing I'm going to do is I'm going to factor it out. So y equals, numerator is not factorable, but denominator definitely is. So x minus 3 times x minus 1. Okay, looks like I can't really cancel anything. Would you agree with that? But I do recognize that, hey, you know what, from first semester, I got 2 vertical asymptotes. X equal to positive 3 and x equal to positive 1. Okay. It didn't ask for these, but I'm going to write it down. So it says, hey, find the point of discontinuity. Well, you have asymptotes. So remember, these are called infinite discontinuities, right? So we're going to spell it out. We have and yes, you do need to tell me the type of discontinuity as well. Okay, infinite discontinuities when x, so at x equals 1 and x equals 3. I'm just putting these in order from smallest to biggest, therefore box that up now that we know the type of discontinuity. Okay, now when do we have a hole? In this case, we don't have a hole, so let me just spell this out for you. We have a hole, start, hole, if the numerator cancel with the denominator. Okay, that's the only time we're going to have a hole. All right, and that's the only time we're going to have a removable discontinuity. Okay, next one. All right, remember this function that we were talking about? So let's graph it out and list the type of discontinuity for this. So we're going to make a chart, all right? We know it's undefined at 0. So at 0, we're going to have a hole. So here's my chart, x and y. Okay, when x is 0, we know that's undefined. So at 0, 1, this is all by 1, okay? But when x is very, very close to 0, I do have a value. But the next integer is going to be positive 1. When x is positive 1, right, divided by absolute value positive 1 is 1, so that's going to be 1. So I know it's going to be a close dot right here. But that doesn't mean these right here don't exist. They do exist, except here at 0. So all of these are okay. How about when x is negative 1? Negative 1 on the top divided by absolute value of negative 1 to positive 1, so therefore it's negative 1. So here it should be a closed dot, but from here to here, again, similarly to the top, it does exist, right? Like half, okay? You're still going to have a value. A half divided by half is going to be equal to negative 1, or a negative half divided by positive half, okay? So this is what it looks like. So anytime you have something like this is a similar graph. So as you can tell, there's a jump, right, from at 0. So this type of discontinuity is called jump at when x is at 0. Okay, how easy that is that? Okay, so next we have what's called a piecewise. Okay, so now if you look at our list, okay, so look at our list. A piecewise, usually have a couple of things, right? You want to look for holes or you want to look for jumps, okay? So piecewise, okay, look for holes or jumps. All right. All right, so here we go. Let's talk about, looks like there's zeros not included in this piecewise function. So we know we're going to have an issue, okay? So let me just, since 0 is not included in f of x, light bulb goes on, right? Issue at x equals to 0. I mean, that's really what we need to know. So let's find the limit on, so find the limit. The limit as x approaches 0 from the right, okay, of this particular function. So I'm going from the right, so that means we need to look at this piece. Would you agree? Okay. And why am I looking at this piece? Okay, so let's sketch it out if you don't know what I'm talking about. Okay. This is a line, so when x is 0, I would have a -1 not inclusive. So here's -1. The slope is going to be 3, rise over run, so 3 over 1. So 1, 2, 3 over 1. So this is what it's supposed to look like. All right. This is going to be an exponential function reflected over the x-axis. When x is 0, not inclusive again, e to the 0 is it's 1. 1 times -1 is going to be -1, not inclusive, which I do have this right here. When x is going to be 1, I'm sorry, no, this is less, so x is -1. So e to the -1, so let's spell this out. E to the -1 equals 1 over e, right? That's sort of how we want to make it positive. But multiply by negative, so it's going to be a -1 over that. And e is about 2.718, so it's about a -1/3. So let's, for the graphing purpose, okay? All right. So I'm going to have when x is -1, I'm going to do right there, right? And then when x is, let's talk about e to the -2, because I'm going to the left. And I need to multiply by negative here because it's reflecting. Okay, so times that by negative, so 1 over e squared, which is really, let's just get a calculator. I don't need an exact value. Okay, that's really not my point. But just for graphing purposes, just to see where it's supposed to go. So second e to the 2, that's 7.38. So -1 over, let's say about 7. Okay, so it's getting closer and closer to 0. All right. Getting closer, so -2. So it's gonna go look like this. Would you agree? Would it ever touch 0? Okay, let me ask you that piece. Would this ever touch 0? Would it ever touch 0? Yes or no? No, we have an asymptote right here. Horizontal one, which doesn't really matter. Horizontal asymptote does not matter with discontinuities. Okay, all right. So this is what we're supposed to have. So the definition, we're going to go back to formal definition. As the limit of this function coming from the right, okay, approaching 0, okay, would you agree that I'm going to have the limit is -1? Now we're also going to do as the limit as x approaches 0 from the left. Okay, from the left. Oh, it's also at -1. Now, f of 0 does not exist. Would you agree? Okay, so all of these are different tests that I'm trying to do. F of 0 does not exist. So, let's go back to some definitions here. First, okay, would you agree that if continuous, if the limit, okay, the limit left and right does equal to f of 0. In this case, this is not true. So we're going to go over to some things here. Removable whole, okay, when f of x does exist, but not equal to f of c, which is true in this particular case. Okay. And again, whole is not always removable, just sometimes, because it's a whole, but it's not removable, okay? So since this fits the definition of whole, removable, we're going to have, spell it out, we have a whole at x equals to 0. All right? And this is pretty much where I'm going to stop for today, because this is 30 minutes. Have a good day, and I will see you guys in class.